Welcome to the lecture of linear algebra. In this lecture, we'll talk about the physical significance of determinants. We have already seen the utility of determinants in finding the inverse of the matrices and subsequently to the solution of system of linear equations. Here today we'll see determinants as nothing but representing the area and the volume of spanned by the matrices. Okay, now we can start with a 2 by 2 matrix, which is a form like this, and as we have already discussed earlier, that if vectors in this matrix are not linearly dependent, we can always reduce this matrix into reduced echelon form, which it could be like this, right? Here you can take A out and D out as well, right, to represent 1 and 1 over here. But anyways, we can represent the vectors in this matrix as A1 and A2, right? So the A1 vector, which is A0, can be given on x-axis, which is A0, and similarly you can think of 0D as the point over here. So if you know that A is in R2, right? So it means two axes or two dimensions will actually be enough to represent those vectors. So if you look at the conventional method of adding vectors, so we can think of this one as A and the vector A1 here, the vector A2 here, right? So we add it up here, we get this resultant vector. Similarly, A2 here and A1 here, right? So it actually forms a parallelogram. Okay, now if you look at this parallelogram, right, this is actually the area of this parallelogram is nothing but A times D, right, which is area of this rectangle is A times D. Okay, now if you start finding the determinant of this matrix A, this is also A times D. But since here we are saying that the determinant represents the area in this case, so A, looking at the sign of A and D, we have to put a magnitude sign in for determinant of A, because area is always positive, right? Now similarly, if A is a 3 by 3 matrix, it will exist in R3, right, and what will generate is a parallel piped, and which will be determined of course by the columns of A. In this case, A1 is equals to A1, A2 and A3. Okay, now since we have already discussed the properties of determinants, and in properties of determinants we have seen that if you add a multiple of one row or column to another row or column, right, it doesn't change the determinant of the matrix, right? Now you can ask quickly, the one thing that comes straight away in your mind, right, that since we are manipulating vectors in the matrices, and determinant is representing the area of the volume of these vectors in that matrices, so why would adding one row, one column to another column will affect the determinant? We have already seen that it will not affect determinant, and in this slide we want to show you that this is really the case, and we want to show you the geometric interpretation of this property, right? So we can think of a matrix A, which is composed of two vectors A1 and A2, right? So A1 is on this axis here, okay, and we assume that there is a line that is passing through this vector, which is L. Okay, now if this is a vector A2, right, this is a vector A2. Now if I add A1 to A2, how I get here is A1, A2, and similarly I have A2, I can add A2 plus A1, and I can see this kind of parallelogram here, right? Now, so when we do the row operation or column operation, what we do is basically add a multiple of one row to another row, right? And that we can do to generate zeros in a column or zeros in the row to actually reduce the amount of computation for the calculation of determinant. So one of the row operation or column operations you can do is add multiple of one column, in this case a1 multiplied with c and add it to a2, right? So since as we have discussed earlier, this is mathematically we have shown that this does not change the determinant of this matrix A, right? So to see that graphically, right, so what we do here is we assume that this is the kind of scaling we did on A1 here, right? And once we did that scaling, we added to A2. So if this is C times A1, right, so if I add A2, right, to this one, right, the resultant vector, this vector will touch over here, some point over here, right, this point over here, right? So what we have to draw is a resultant vector of this a2 plus c times a1 will be nothing but equals to this vector over here. Okay, now similarly we can carry out another vector addition. Order of vector addition can change. We can say c times a1 plus a2, right? So again this is c times a1 plus a2, this point here, and again a2 plus c times a1 will get you as a2 here and c times a1 here, so it will land up to the same point here. So the resultant vector, this is the resultant vector here. Okay, now what we have to do is now add a1 to that resultant vector, right? So this is the resultant vector. So if I add a1 here, so I will reach over here, and this will be my new parallelogram determined by these vectors. Okay, so this is the second parallelogram that I have. What I want to show you is they both have the same area, because this matrix, determinant of this matrix, if I call this a1, let's say, and this called matrix a2, determinant of a1 in this case would be determinant of a2. Okay, now so if you see here, if this is a line that is passing through vector a1, and if I add a vector a2, right, it means this a2 plus l will be parallel to this line. Okay, this a2 plus l will be parallel to this line over here, right? And now what I've seen here is this point a2, right, which is over here, or in this case over here, for example, right, have and has a perpendicular distance to it as L, right? So the amount of distance that you have from either this point to this point is L. Similarly, the resultant vector of this thing here also has the same distance as L, right? So as we know that because the bases are same, and both the points that we have on the parallelogram in one, so this is the first parallelogram which was for this one, and the second parallelogram for this one, the points that they have actually have the same perpendicular distance to the base here, right? So once they have irrespective of their tilt, once they have the same distance to the base, right, they will always have the same area that we know from our basic understanding of parallelograms, right? So it means this, the area 1 is same as area 2. So we can actually say that let a1 and a2 be the non-zero vectors, then for any scalar c, the area of the parallelogram determined by a1 and a2 equals the area of the parallelogram determined by a1 and a2 plus c times a1. Okay, now so now we can actually similarly demonstrate this for 3 by 3, that if you have a 3 by 3 matrix and you are doing the row and column operations to ease out the calculation of determinant, right, it will not affect and change determinant. So why it doesn't? Let's see that in this slide. Say for example, now if you have a matrix, let's say like this one, A, B and C, right? So we know that from extending the concept from R2 to R3, right? So we can represent this vector here on x-axis, this on y-axis, and this on the z-axis, right? So this point here is A00, 0B0, and 00C, right? So the volume, we can now write it as the sum of the corresponding vector. So this point, this side represents, this point represents the addition of this vector and this vector, this parallelogram, and this parallelogram represent addition of this vector and this vector. Similarly, this side will also have addition of this x vector and the y vector, x vector and the z vector. So what you will have is, in this case, a sort of cube to represent the volume spanned by this or drawn by these vectors. Now we know the determinant of the volume of this parallel pipe is actually nothing but the height, the length, width and height. So that is nothing but A, B and C, right? And if you take the determinant of it, that is also A, B, C. So in fact, if I take the mod of it or the magnitude of it, because volume is always positive, right, both will represent the same thing over here. Okay. Now for any arbitrary 3 by 3 matrix which has A1, A2 and A3 its vector, we can now show that that if you add a multiple of one column to another column, this will not change the determinant as well. It means the volume spanned by these addition of these vectors. Now you can think of again going back to the last example here. We established that that the perpendicular distance does not change from point A2 and A2 plus C times A1, right? So similarly, we can actually show that over here as well, that if I add to be exact here, so if I add say if I add multiple of A1 to A2, right? Now I can think of to visualize that, what I can do is make a span of A1 and A3, right? So if I make a span of A1 and A3, right, so this is the bottom, so this is the vector, this is the vector A1, okay, this is your vector A2, right, and this is your vector A3, okay. Now the thing here is, if A1 A3, if I make a span of A1 and A3, so that will be the bottom floor here, which is given over here, right? So I'm drawing that with my hand over here. So this is span of A1 and A3, right? Now if I add another vector, which is A2 times initially let's say add only A2, right? So if I add A2, simply like in the previous case we had the line, we will now have a plane over here. The plane will be parallel to another plane which is passing through A2, right? So this is the second plane which is passing through A2 over here, right? So now again we can see that whatever the values we put A2 plus C times A1, it will always remain in the top layer, right, and always have the same perpendicular distance to the bottom span of A1 and A3, indicating again the same observation from the parallel pipe, that if the perpendicular distance remains the same, of course the volume will remain the same, right? Either you adding generating this volume by A1, A2 and A3, right, or either you're generating this volume by A1, A2 plus C1 and A3, okay, everything will remain the same, because any vector A2 plus span of A2, A1, A3 will be in this top plane. Or if I add A2 plus C times A1 plus span of A1 and A3, right? So it will also be in the top plane, and since the span here is the bottom part over here, any vector that is A2 plus CA1 will have the same perpendicular distance to that span, and because it has the same perpendicular distance to the span, it will not change the volume of the parallelepiped by this vector operation. Okay. Now, similarly, to conclude here, we can now think determinants as the one that can be calculating, at least for R2, calculating the area, and for R3 as volume. Okay. Now, for higher dimension, of course, visualization is quite difficult, and we probably won't be giving any specific names to the determinants. But for at least the visualization of 2 by 2 and 3 by 3 matrix, you can say that determinant of 2 by 2 represents the area, and 3 by 3 matrix represents the volume. Okay. Now let's look at very another important concept that that deals with the determinants and its interpretation regarding area and the volume. If you remember that we have studied transforms in the, I think, first chapter, and when we in the second chapter actually. Now, linear transformation. So we said that if there is a vector x in a certain domain, in a certain region, we can actually transform that matrix by transform that to another region by the transformation governed by this matrix A, right? So in general, if I say that if T is the transformation, let's say from R square to R square, so determined by a 2 by 2 matrix, then if there are a set of vectors that draw a parallelogram in R square, right? So if S, you say S is the domain, then T of S is basically the image or image under the transformation T, right? So it means if S is a domain, right, and there's a parallelogram over here spanned determined by certain vectors, right? What will happen if I apply transformation to those vectors, and when I apply the transformation to those vectors, right, so it means their position will effectively change, their image will be different from the one that they have in S. And I want to find what is the relationship between the area or the volume of in S and TS, right? That is, if this parallelogram has a certain area, what will be the area over here when I transform it using T of S. Okay. Now, in general, we can say that if S is a parallelogram in R square, then area of TS, right? Area of TS, that means now this vector has their images in vectors in S has their images in T of S, right? It's nothing but determinant of A, and the area spanned by the vectors of the transformation, and the area of these vectors in S, right? Now, similarly, if T is determined by a 3 by 3 matrix, and if S is a parallelepiped in R3, then the volume of TS is nothing but determinant of A times volume of S. So it is quite intuitive and logical, right? Now, assuming, let's do an example to illustrate that what we have just said, right? Let A and B the the positive numbers, and what you have to do is find the region, find the area of the region E bounded by the ellipse, whose equation is x1 a square plus x2 square divided by b square equals to 1, right? Now we can think of ellipse. We can actually make an ellipse by transforming a circle. Now, so remember, if this is a unit circle which has this has one side, this has one. Now, what will ellipse will be? Ellipse will be that if I have unequal scaling on x-axis and y-axis, right? So it means I want to shift this point to a point A, right, and I want to shift this point to a point B. Okay, now of course this will be minus A, and this of course this would be minus B, right? So we, as we know that we had done in transformation as well, right? So we want to have this one, think of this this u1 by scale by an amount A, and we don't want to have any other kind of increase while we were doing this scaling, right? So it means I can make this as something A0, right, because I don't want any scaling on y-axis while I'm scaling x-axis. Similarly, while I'm scaling y-axis, I don't want to scale x-axis, so it means I can have 0b. So this is actually a transformation matrix that can so if there is a circle in S, right, so this will be actually the transformation, the image of these vectors in T of S. So you can think of this vector, this point going here, right? So this is its image under transformation. This point is image under that transformation. This point is image under that transformation, and this point is image under that transformation. Okay. So what we want to do is to find the area of this ellipse, right? That we have actually drawn by transforming this circle, right? Now we know that transformation, because we have now calculated the transformation matrix, so we know that if x is the new x becomes A times u. So u was the axis in for the circle, and x was the axis here for the ellipse, right? So the scale, actually x is scale on. So u1 and u2 here are the vectors in for the circle, and x1 and x2 are for the ellipse, right? So transformation, you can write it as x is A times u, so A0 0b, and we know that that can only happen because this exactly have to be calculated at this point, right? So it means u1, this axis will be scaled by A, right, and of course the other axis will be scaled by B. So u1, we can always say that x1 by A, and u2 is always x2 by B, right? So we can actually at those points we can actually find your transformation from x is equals to A times u, right? Okay, now since we have the area, we know the area of this circle, which is nothing but pi r square, and we know the transformation matrix, which is A, and we know its determinant, which is nothing but A times B, right? So the area will now becomes AB times pi r square, and r is here is because of the unit circle, is nothing but equals to pi times A times B. Okay, now similarly, to do another example, let S be the parallelogram determined by the vector b1 and b2, and let the transformation be the matrix A. So there are two vectors in S, b1 and b2, and they're actually adding up to make a parallelogram. So now what you have to do is compute the area of the image of S under the mapping x to Ax. Now straight away we can actually find the determinant of A, which is 2 times 2 minus 0, and that will be 2 here, determinant of that, and of course you have to take the magnitude here, right? Now similarly, because so you can think of this two matrices b1 and b2 as 1 3, putting here b1 and b2, so 1 3 and 5 1. Okay, so determinant of this S will be nothing but 1 minus 15, comes out minus 14, but remember you have to take a magnitude of it because area is always positive, so when you take the magnitude of it, that becomes 14, right? So the area of the image of S under the mapping, we know the formula, the determinant magnitude of determinant of A into magnitude of determinant of S, that is nothing but 2 times 14, which is equals to 28, right? Similarly, we can actually use the properties of determinants to solve some of the exercise problems. So if let's say we've been asked to find the determinant of B4 and B is that matrix, right? So remember that determinant of A times B is nothing but determinant of A into determinant of B, and determinant of B4 from that logic will become determinant of B square into determinant of B square, and that I can again determinant of B square can be written as determinant of B into determinant of B and determinant of B into determinant of B. So that means I can write this as the whole to the power determinant of B whole to the power 4. And to find out determinant of B, what I can do here is I can open from that side over here, so I can write minus 1 1 plus 1 1 into, so what I'll do, I'll remove that row and the row column, so that is I'm left with 1 2 2 1. Similarly, go find the cofactor from 1 2, which is actually 0 luckily, and then I can similarly find the cofactor from the first row and the third column, which is 1 1 1 2. And similarly you can see here this will come out to be minus 3, and this will come out to be 1, and if you add them up, it's minus 3 plus 1, which comes out to be minus 2. So determinant of b to the power 4 will become minus 2 to the power 5 and minus 32. Similarly, we can do another example. So let us be again it's more of a repetition of the previous example. So let us be the parallelogram determined by the vectors this one, and the transformation here is given by A. So what we can do here is to find the determinant of this A first, which is, and then take the magnitude, which comes out to be, say, 12 minus 6 will comes out to be 12 minus 9, that comes out to be 3. And similarly these vectors in S which are over here is b1 and b2, and you get minus 2 3 and minus 2 and 5. So what you do here is find their determinant as well, right? So it comes out to be minus 10, and you get here is plus 6, which comes minus 4, but you have to take the magnitude. Remember that area is always positive here because it's a 2 by 2 matrix. So 3 times 4 here is the area of the image of S under a transformation. So what you have done is transform these vectors in S, which is b1 and b2 vectors in S to another set of vectors, right, in T of S, right? So you can say this is probably the parallelogram made by, I'm just giving a rough sketch here, right here. So it means this is your S, this is your A times transformation of S. So that is going from here to here. You might have a different parallelogram, right? Sorry, not a very good one, but anyways. So this might have a different area. So in this case you find out that the area that was there in domain S was 4, but once you transform that area has increased as 12. Similarly, if you look at that example that we have done previously, right, the area was the area of the circle is actually pi, right, but the area of the ellipse is, if A is greater than 0 and B is greater than 0, you will have this as greater than pi, right? So it means you can actually scale the area by the transformation as well, right? So you can compress this space, or you can basically expand this space under transformation. Similarly, if you've been asked to find the volume of a parallelepiped with one vertex at the origin, adjacent vectors at the falling region, what you have to do is write them in matrix form. This is the first vector, this is the second vector, and this is the third vector. So you write first vector, second vector, and third vector. You try to find the determinant of this, right? I have opened it from that column, right? So that comes out to be minus 1 plus 1 into, so this is the first one, and its cofactor expansion is 2140, right, which is written over here. In the second one you have this row bin out, this column bin out, comes out 1540. Of course you have to do the minus calculation as well, and then you have minus 5 in the third side is actually minus 3, sorry, minus 3, this is minus 3 into minus 1 to 3 plus 1, and of course when you do that, this one here and this one here, it comes out 1521. So this second one is luckily 0, right? I can do the calculation over here, which comes out to be minus 4, and then it comes out to be minus 3 times 1 minus 10, and of course that comes out to be overall minus 4 plus 27. If you add them up, that comes out to be 23. So it means the volume of this parallel pipe determined by these 3 vectors, right, is actually 23. Now to verify that it actually representing the volume here, right? So what I want to do is to find the volume of this parallel pipe, these in a conventional method of finding volume, right? So you might have you have a formula of the volume of parallel pipe. You can go and search for that, and when you find that out, right, which is, I think, is a the base into width into height times cos of the angle between the base and the height, right? So if you try to find it using that formula, you will find that you will end up at 23. So this is an assignment that you should carry out yourself and verify that the volume of this parallel pipe that you calculated from the determinant is same as from the one you calculated from the conventional method, right? Okay, now there was another question that we that I want to demonstrate here is it's regarding this exercise 9 and 10 at the end of this chapter, in which there are 2 matrices which are called Bender-Monde matrices. Number 1, first of all, that you have to show that that determinant of T is nothing but B minus A, C minus A times C minus B, right? So what you can do here is because I have this 1 on that side, I can use that to remove this 0, to make these zeros over here, to make these 2 entries as 0. So I can able to expand this along this column, and then to easily calculate my determinant. Now, so if I do that, right, so what I do is I subtract the first row from the second row, and again third row from the first row, right? So when I did the first operation, I got here is 1AA square, and subtracting the first row from the second row, 0 B minus A, B square minus A square. Similarly, if I did the same with the third row, right, so it comes 0 C minus A and C square minus A square, right? And then when I actually open it up, did the cofactor expansion from this point here, right? So I found that it's 1 into 1 is 1 into 1 plus 1, and again I have this this row is removed, this column removed, and you will have left with this thing here, B minus A, B square minus A square, and C minus A and C square minus A square, right? So in the first column, to simplify my calculations, right, I can take this B minus A out from that row, and again I can take the C minus A out from that row, right? So eventually I've left with here is B minus A into C minus A, and you have got 1 into B plus A over 1 into C plus A, right? So this is quite easy to calculate, right? So multiply both of them and multiply them here, and just take the subtraction of it, right? So C plus 1 A minus B plus A comes out to be C minus B, right? So we can see here we have already proved that this is actually the determinant of T, right? Now in the second part of this question, right, what we want to do is to show that that f of t, which is nothing but determinant of V, with x1, x2 and x3 having distinct values, explain that why f of t is a cubic polynomial. So it means if I have this matrix V of t, right, what I have to show here is that its determinant, if I take this determinant, it is a function of time, and it results in a cubic polynomial, right? In order to show that, you can see here that if I expand it from the first row, right, that can give me an easy interpretation. Cubic polynomial means that you have this f of t as c0 plus c1t plus c2t plus c3t cubed, right? So it means it is much easier to expanded from here. So when I expanded from here, right, so I can thought of this one as C expansion from this cofactor. So I have got C naught as x1 square, x1 cube, x2 square, x2 cube, x3 square, x3 cube. Similarly, when I do the second expansion from second cofactor expansion from here, I will have 1 x1 square, x1 cube, 1 x2 square, x2 cube, 1 x3 square, and x3 cube, right? Now, what it didn't, this question didn't ask us to calculate all the coefficient. It just asked us explain why f of t is a cubic polynomial, why it's a cubic polynomial, and show that the coefficient of t cube is non-zero. So I mean, if we have to show that f of t is really a cubic polynomial, we need to show that c3 is actually non-zero, right? So if you open it up from the concept of c3, so it means that is I can open it up from here. So the answer, the result will become 1 x1 square, 1 x2 square, 1 x3 and x3 square, which is written over here. And of course you have to take care of the sign in the cofactor expansion, which is minus 1 times 1 plus 4. And of course there is, because we are taking this as the multiplication of 2 cube, right? So this cofactor expansion is actually, it's nothing but c3. I can write the c3 t cube equals to this thing here. Okay, now if I do that, right, we have already solved this kind of form in the previous exam, right, which is over here, right, that if we have this kind of form, which is given over here as t, right, 1 x1 square, 1 x2 square, 1 x3 square, right? We always have a determinant which is b minus a, c minus a, and c minus b, right? So equating a as x1, b as x2, and c as x3, we'll find out the determinant of this one is nothing but equals to x2 minus x1 and x3 minus x1 and x3 minus x2. Okay, now this marks the end of this chapter. If you have any questions, any problems that you need to discuss, please you can message me, you can email me, you can have your you can add a comment on the YouTube link that I will give it to you, or you can have you can send a voice message to my WhatsApp, right? So I'm quite hopeful that you are grasping the content that we are discussing in these online video lectures, right? So thank you. Allah Hafiz. Welcome to the lecture of linear algebra. Today we'll talk about vector spaces, and actually the chapter 4 of the book that we've been following in this course. So we have already discussed a bit of vector spaces in our previous lectures, but in this chapter we will discuss the various aspects and detailed aspects of vector spaces and subspaces, right? So generally, to define it, a vector space is, as we have already discussed, a vector space is actually a non-empty set V of objects called vectors, right, on which are defined two quantities called addition and multiplication by scalars, by real numbers, and it is subject to 10 axioms and or rules, you can say, that it must follow for that addition and multiplication, and it must hold for all the values or all the vectors that you have in the vector space, right? So because it's a collection, right, remember it's a collection or it's a set of the vectors, so we can think of three vectors u, v, and w to define the axioms of this vector space. The first axiom is that the sum of two vectors, any two vectors which are already in the subspace in the vector space, should be in V, right? And similarly, two vectors, when the order of sum is changed, they yield the same result. And third one is that if you have three vectors and you add two vector first and add the third one later, is equals to you add the second and the third one first and add it to the u later, right? So the fourth one is that the zero vector is in V, such that if you add 0 to another vector, it will result in in u straight away. Now, for each u in V, there should exist a vector that if you add that vector, it should sum up equal to 0. So u plus minus u should be equal to 0. Similarly, if you multiply any vector c by u, then cu should also be in V, right? So similarly, if you multiply any scalar number to the sum of two vectors in the vector space, their output should be as like that you have multiplied these vectors individually by c, right? Similarly, if you have some two scalars and you multiply with the vector, then of course it will comes out at individual scaling for those vectors, for this vector. And again, similarly for the multiplicative property here, which is cdu, so if you have scalars have been multiplied rather than added in the 8th exoime, it has been multiplied here, right? So you yield the same scalar multiplication factor. And then the 10th one is that if you have there should be a unit vector that if you multiply any vector with that vector, the vector should yield itself, right? So this was the last exoime. So 10 exoimes that vector space should follow while for a vector space. Now there could be many examples of vector space. One of the simple example is Rn for r greater than 1. So it means r square, r cube, r4, and so on and so forth are examples of the vector space. In this course we're talking about the real vector space, though the same kind of observations are equally valid for a complex vector space. Okay. Now the second example vector space is a set of all infinite sequence of numbers. So if you have y of k as a sequence of numbers which is existing from say minus infinity to infinity, or so this could be an example of a vector space, right? So similarly, if there is another infinite sequence and you add them up, right, it should follow the property of it should follow the 10 exoimes of the vector space, right? Or so in this case, if z of k is another element of S, then y of k plus z of k is the sequence that is y of k plus z of k, which can be actually written like that one over here. Okay. Now similarly, if you multiply this as by constant c, so all these values or sequence elements should be multiplied with c, which is also one of the exoimes of the vector space, right? Now this kind of this infinite sequence of numbers actually occurs in when you talk about signals, and signals we know have in electrical engineering has a lot of utility because they are used in signal processing, in speech signal processing, in communication systems, in control systems, right? So I mean, you can think of a signal that is moving along this axis, or time axis. Let's say you can say this as time axis, right? So if I sample the signal, right, so I mean I'm not taking a signal value at every possible point. So if I sample the signal at some different points, right, so I can this case say that t is equals to k times t. So I'm sampling the signal by after some amount of time. So this could be k is equals to -2, this would be k is equals to -1, k is equals to 0. So y of k could be the set of values that you have for that signal at these instances, right? So you will see a lot of this in probably your 4th and 5th semester, right? You start interpreting the vector spaces as the discrete time signal as the vector space, right? Now similarly, one of the example of the vector space is the set of polynomials of degrees of degrees at most, let's say n. We say it's Pn, right? So if p of t is a polynomial of nth order, right? So it exactly follows the same law. So if q of t is another polynomial, so p of n is actually a vector space. So if you add p of t with q of t, right, so we will have the sums a naught plus b naught plus a1 b1 t plus 1 and so forth. Similarly, if you multiply c with p of t, of course all these coefficients will actually get multiplied with this c, right? So which actually follows the exomes of the 10 exomes that we just discussed in our previous slides. Similarly, in practically, we are not interested in the whole vector space. We are actually interested in appropriate set of vectors form some larger vector space. For example, the examples that we have just covered, like for example in this case, we are interested in one of the polynomials, right? We have so we may be interested in the polynomial of order 3, right, up to 3, right? Or we may be interested in some particular kind of function, certain kind of polynomial function. Similarly, we may be in the case of signal, discrete time signal, we may be interested in some specific values of y of k's, right? So not always, we are not interested from the all possible set of values. We are interested, may be interested from the values from -10 to y10, right? Or the range of the amplitudes that we may be the point of consideration. We say the amplitude should not be greater than certain amount or should not be less than certain amount. So we are not often, more practically, we are not interested in spaces, infinite spaces. We are actually interested in the appropriate number of or appropriate subset of vectors from some larger vector space. In order to deal with those spaces, right, we restrict, we don't have to exactly prove all the 10 exomes. Three basic exomes that should be included in that subspaces is the first one, in which the zero vector of V, if we say H is a subspace of some larger vector space V, the zero vector of V should be in H, right? And that if that subspace in that subspace, this must be closed under addition, and it means if there are two vectors in that subspace U and V, their addition should also be in H, right? And similarly, if there are two vectors, if there is a vector U, and if you multiply that vector with C, the result of CU should also be in H, right? So these are the three exomes that the factors in subspace should follow. And if those vectors follows these exomes, the vector space that formed by these vectors, we will call that as subspace. Now similarly, you can say that the if P be the set of all polynomials with real coefficients, then as an example we can say P is a subspace of all real valued functions defined on R, right? So say for example, for function each n greater than 0, Pn is the subspace of actually P, right? So P if is a set of polynomials for all possible real coefficients, right? So in this case we can say the Pn that we have is a subspace of this larger vector space P, right? Now one of the most important thing that we should consider that is that vector space R2 is not a subspace of R3. Similarly, it means a vector in R square can be written as AB, but and a vector in R3 is written as A, B, and C, right? So there is, since you have to remember that H is in V, right? So H vectors are some subset of vectors in V, right? So A, B, C, AB is not a subset vectors of ABC, right? Because the factor is you cannot generate C from this vector here, or I mean it is not in the same dimension as V, right? So because H is a some portion of V, a subset of an appropriate subset of vectors, right? So So these vectors can exist in V, only those vectors can go into H, right? So this kind of vector does not exist in R3. So this vector does not exist in R3, so it means it cannot be the vector, it cannot form a subspace, right? So in reality the vector space R square is not a subspace of R3. Similarly, for this can be generalized, right? So R n minus 1 is not a subspace of R of n, right? So on and so forth. So another important observation is that if there is a plane in R cube, or say R square, is not passing through the origin, it is not the subspace that does not pass through the origin. It's actually cannot form a subspace, right? So it means a subspace has to have a zero vector given from the first exime of the subspace, right? So as we have seen earlier, right, the most common way of defining a subspace is by span, as we have discussed that in previous lecture as well. So we can simply define a subspace by the span of V1 to Vp vectors. The all possible set of linear combinations of this vector actually will form a subspace. It means it will follow the first exime, right? So that C, if all C's are 0, it means 0 vectors in 0, and similarly addition of that will also be in that subspace, and so on and so forth, right? So to give an example of that, right, so let's say if let H be the set of all vectors of the form a minus 3 b minus a and b, where a and b are the arbitrary scalars, show that H is a subspace of R4, right? So we can write that as this thing here as a minus 3b, b minus a and b, right? And we can separate out a and b. So we've got here is two set of vectors, v1 which is here and v2 over here, right? So it means a times v1 and b times v2, because a and b can arbitrary numbers, right? So it means it represents all possible linear set of combinations spanned by the vector v1 and v2. So it means we can say that H is nothing but the span of v1 and v2. And from the discussion, because you know that zero vector should be in H, right? So it means if a is 0 and b is 0, right, the H will also have a zero vector. So in essence, right, so it means these vectors will span will define a subspace, right? Similarly we can do another example over here in which we can discuss that if certain vector is in this really the part of a subspace or not. So for what values are, for example, there is an example here. For what values of H will Y be in the subspace of R3 spanned by the vector? So V1 and V2 are the vectors that can span a vector as a subspace. V1, V2 and V3 are the vectors that can span a subspace. So we need to find out for what values of Y, for what values of H, this Y vector will be in the subspace, right? So if you remember this kind of problems, you remember it is equal to finding finding the consistency and inconsistency of the solution, right? So in essence, right, what we do in those methods, right, we make an augmented matrix. So this is a vector v1, v2 and v3, and we augment Y over here. So once we did a simple set of calculation, row manipulations and calculation and some row operations on this matrix, we can actually transform that matrix to an echelon form. So it means to do that, right, what I can do here is add the first row to the second row. If I did first row second row, the answer becomes 0, 1, minus 6, minus 2 and minus 1, right? Similarly, I can multiply the first row by 2 and add it to the third row. That becomes minus 2 plus 2, 0, right? So 5 multiplied by 2, 10, and you add it minus 7 comes 3. you add the first row minus 6 and you have 0 here, so it comes out minus 6, and what you add is multiply minus 4 with 2 and add it to h, it becomes minus 8 plus h, right? Similarly, what I can do here is now reduce that form further. I multiply the second row with 3 and subtract it from the third row. So when I do that, right, so it means that if I multiply that, so I have this as this comes out at 0, and what you have is 3 minus 2 6, and minus 6, and you subtract minus 6 again, comes out to be 0. And again in this thing here, so you multiply with 3 here, so minus 3, minus 8 plus h minus 3 becomes plus 3, so minus 8 plus h plus 3. So it means if really it is really in the subspace of if y is really in the subspace of these vectors v1 and v2 and v3, it means the solution has to be consistent. It means this has to also be 0, right? So minus 8 plus h plus 3 should be equal to 0, and the values that you get, h is equals to 5. So it means if the vector y is equals to minus 4 3 5, that will definitely be in h, okay? or the vector subspace formed by v1, span of v1, v2 and v3. Now similarly we can there's a problem in the exercise that we can actually solve. So let h be the set of points and on the unit circle in the xy plane, that is h is the subspace, had we saying is the space that is formed by values of x and y for which x square plus y square less than or equals to 1. So it is on the circle and inside the circle. So all these values that are on the circle and inside the circles are actually defined is defined by this equation over here, right? So we have to find a specific example to show that h is not a subspace of R square, right? So there is no way that this area that is defined by this h is actually a subspace, right? So you have to remember 3 properties of a subspace. First one is the 0 vector should be in the subspace. So if the 0 vector is in subspace, it means it is satisfied, because if you look at this diagram over here, 0 vector over here is in the subspace. Now let's look at the second property, in which you have to have that your addition of 2 vectors should also be in that 2 vectors that are in h, right, should also the sum should also be in h, right? So it means if I take these vectors u as 0.5, 0.5, which are in h, right, over here, and v as 0.5 and 0.6, which is also in h, right? So if I add u plus v, you find out that this will not be in h, because 0.5 plus 0.5 will comes out as 1, and 0.5 plus 0.6 will come out as 1.1, right? So it means this will be out of this region, right? So the second axiom is not satisfied. Similarly, remember that if you take a vector in h, right, if you multiply with some constant c, right, in this case I've taken the vector as 0.5 and 0.5 and multiplied with 4, the answer comes out to be 4 into 0.52 and 4 into 0.52. So it means 2 vector is also not in this h, right? So it means h is not a subspace of R2, right? Similarly, there is another problem that is given in the book is an example of a mass spring system, right? So if what it says is that if a mass is placed at the end of a spring, and if the mass is pulled downward and released, the mass spring system will begin to oscillate. That's a common observation that you must have seen in engineering physics. The displacement y of the mass from the resting position, so it means this was the spring, the mass attached to the spring, and it was in resting position. So when you pull it down and just let it go, the displacement y actually can be written as c1 cos of omega t plus c2 sine of omega t. So where the oscillation frequency omega is constant and depends on spring and the mass. So what we have to show that the set of all functions described by this equation over here, the displacement equation, where the omega fixed and c1 and c2 arbitrary, is a vector space, right? So in order to do that, right, so if you look at this problem here, we can now y of t c1 cos of omega t c2 sin of omega t. So I can actually think of this one as x as cos of omega t and sin of omega t, because they represent different x's, right? So they are orthogonal to each other. So it means any vectors they form here is effectively orthogonal to each other, right? So I can write this as y of t is equals to c1 cos of omega t 0 plus c2 into 0 sin of omega t, and you can write this as nothing but the span of cos of omega t and sin of omega t. And because you can write this as two set of independent vectors as the span, right? So this is actually a subspace of V, and hence is actually subspace. Now another example that is also exercise problem that is also given in the book. What you have to I think the problem number is 33. What you have to show that if H and K are some subspaces of a bigger vector space V, right? So what we have to show that this H plus K is also is a subspace of V, that their addition of the subspaces also a subspace of V, right? It's another new subspace, right? So we know that if H is a subspace of V, it means it has got a zero vector of V. If V is a subspace of V, K is a subspace of V, it has also got the zero vector of V. So it means zero vectors, it means their sum will also have the zero vector, right? Now in the second case, we have to show that the subspace H plus K, right, is closed under addition, right? So because H plus K is being generated by the addition of two subspaces, so let's take the vectors in those subspaces. So let's say u1 is the vector in H, v1 is the vector in K. So new vector of w1 will be, it's nothing but the sum of u1 plus v1. Similarly, there will be the vector w2 in H plus K, and u2 is a vector in H and v2 is a vector in K, right? So it means if I add those two vectors, right, that sum of these two vectors should also generate the sum in the subsequent subspaces, right? So if I add w1 plus w2, right, I get u1 plus v1 plus u2 plus v2. So I get here is u1 plus u2 and v1 plus v2, right? So it means they will the sum of the subspace, that is the sum of two subspaces, are also closing under H and closed under K, because u1 plus u1 vector is in H, u2 vector is in H, and we know that because it's a subspace, that will be in H, right? So v1 plus v2, v1 is in K, v2 is in K, their sum will also be in K, right? So it means the sum of the vectors here in H plus K will also generate the subsequent sum of the vectors in the subspaces. So it means the second property or second axiom of the subspace is also satisfied. Now look at the third one here. Third property is scaling by a vector. So scaling by a constant, scaling by a scalar. So if I multiply this C by a vector in H plus K space subspace, the answer would be C times u1 plus v1, and you can see that it's C times u1 plus C times v1, because u1 is in H, C times u1 is also in H because the subspace already defined. And similarly, v1 is a subspace, v is a vector in subspace K, C times v1 is also in subspace K because by definition it's a subspace, right? So it means both these vectors are in subspace. It means this vector is also in H plus K, is also in that subspace. So we can say that H plus K is also a subspace of V. So it is clear that if H is a subspace of V of a bigger space, in K is a subspace of some bigger vector space V, their sum will also be another subspace. Okay. Now in the B part of this question, we have to show that H is a subspace of H plus K, and K is the subspace of H plus K. So it means if the opposite, we are asking the opposite question. Previously we were asking if we have H and K as subspace, then H plus K is a subspace of V, but in this case we are saying that if you are given a subspace H plus K, we have to show that H is a subspace. H plus K becomes a bigger space in which S is now its subspace, and K is also now its subspace. Now for easily we can see that because H is a subset of H plus K, because every vector U in H, right, may be written as U plus 0 or U1 plus 0, right? So where the 0 vector is in K, right? And also in H1, since H contains a 0 vector of H plus K, and H is closed under vector addition and multiplication, right, by scalars, therefore H is a subspace of V and H is a subspace of H plus K. And similarly the same argument can be used to justify that K is a subspace of H plus K. Okay, now this marks the end of this topic. In the next lecture hopefully we'll talk about the column spaces and null spaces again. Thank you for listening. Allah Hafiz.